Hey everyone, welcome back. So in this part of the lecture, we're going to throw away even more information and look at unordered samples instead. Okay, so just recall from the last lecture that we let omega be e to the n, where e is set of colors. Okay, and n is number of draws. Okay, and we equip this with its power set. Oh, sorry. Power set omega as sigma algebra. Okay, where we think of this as the sequence of colors that we pick rather than the numbers that we've put on our balls. Okay, so here we have an ordered sample. Now we want to go to an unordered sample. So, well, the way you do that is you sort of put the elements in here and you throw out the order. So, as we've seen previously, a possible sample space that we could use and that we are going to use is where we just count the number a and e. Oh, well, let's write this as an element of z plus non-negative integers to the power of e, where the sum over a and e of ka is equal to n. Okay. So what's the natural probability measure on this space? Well, again, we'll equip this with its full sigma algebra, and we're going to construct another random variable that throws away information. So exactly as we did previously, we went from ordered where we care about the number to ordered where we just remember the color of the balls. Now we're going to throw away the order too. And how can you do that? Well, you map an element in here to how many times color A appears, and that's what you'll call Ka. So let's write that out. So S from big omega to omega hat is going to take S of a list of colors and map it to SA of the color for A and E. Okay. And, well, what does SA do? SA just picks out and gives you a 1 every time an element in omega is color A. So there's a way we write that. So there are n elements here in here, so there's going to be, well, n possible copies of color A balls, and then we use this 1 sub A of omega I. Okay, where this function here is 1 subset A of omega is equal to 1 if omega is in A and 0 otherwise. Okay, this is sort of notation we'll use a lot, and when A is a singleton set, this is just 1 if omega equals the single element of capital A here. Okay, so this just counts up the number of balls of color A were in this sequence, and now we've thrown out the order. So this would be a reasonable random variable to push our probability measure forward with. Okay, so I realized that I didn't introduce notation for the probability measure that we had previously. So recall that the probability measure prob measure on omega with its power set sends a sequence omega 1. Well, this is a finite set, so it's enough to define what it does to a singleton. And I'm going to use this notation, which I forgot to introduce last time, of a singleton. We got 2 ... omega n gives you, well, what was it? So it's the product of rho omega I equals 1 to n, where rho of omega I equals, well, it's the number of balls that are of color omega I divided by the total number of balls. Okay, and you can ignore this notation that I'm using here for the moment, but we'll see later on that you can, as we had products of sigma algebras, you can have products of probability measures, and we'll get back to that later. Okay, so, well, we've got a probability measure on omega, we've got a natural, in some sense, map from omega to omega hat, and because everything is equipped with the discrete sigma algebra, this S is automatically a random variable, so we can consider the push forward of this measure, rho tensor product, rho to the n. Okay, and this will denote p hat. And so, as again, everything here, they're all finite sample spaces, so we can just check what it does to a single element. So suppose K is K A in E is a single element of omega hat. Well, then the probability of the singleton set K is, well, by definition of this push forward, you've got this S of the singleton set K, which is rho tensor product n times of S in K. Oh, yep, that needs another curly bracket. Okay. Well, what does it mean for S to be in K? We can just, well, expand this out based on what rho is here. So this is omega in omega such that S of omega equals K. And then rho tensor product n of omega. Okay, so this is using this step here. We're splitting this set as a disjoint union of all the elements of the singleton sets which contain all the elements of this. And then using sort of finite summability, yeah, over disjoint unions of our probability measure. Okay. Well, we can write out what this part is. This is sum over omega in omega such that S of omega is K times the product from I equals 1 to n of this rho omega I. Okay, but now we know that since S of omega is equal to K, we know exactly how many of these omega I are equal to each. Well, we know exactly the composition of colors in here because there has to be Ka copies of color A and Kb copies of color B, etc. So this part is actually fixed. So we can we find that this is sum of omega in omega with S of omega equals k, and then this is just going to be the product over A in E of rho A to the power of Ka, because there are Ka of color A in here, and then you're taking the product over all the different A's, you're going to recover this thing, which now we see doesn't actually depend on omega. So this is just equal to, well, the number of elements here, since this part here is constant, and then we're just adding up a constant a certain number of times. So this is the same as the size of the set omega in omega such that S of omega equals k times this product. Okay, so what is this? Okay. Well, note here that this is an element of omega in which we only consider the colors. Okay, so first of all, if we start with some omega that's in here, that's in such that S of omega is k, well then if we reorder omega, we're still going to find that S of omega is k, because it just counts the number of each color that's in omega. Okay, so if we start with 1 omega, start with, say, omega 0, such that S of omega 0 equals k. Well, then we've found that we can permute the entries of omega 0 and maintain this. So there are n elements here, so there are n factorial permutations. Okay, but in omega 0, there are also, well, for each A in E, there are Ka indistinguishable balls of color A in any permutation of omega. So we've actually counted too many, because in this big omega we've already passed to just remembering the color. So we can permute these balls of the same color in any order we want. So in fact the size of this set is equal to n factorial divided by the product over A in E of Ka factorial. Okay, and we give this symbol here a name. So, this is nk, and this is called a multinomial coefficient. Okay, so nk is multinomial coefficient. Okay, you've most likely seen the binomial coefficient before, which is where you take k to be a single number. Now k is a vector of numbers which add up to n. Okay, so if you're only looking in one dimension, if sort of the size of E is 2, so that you've only got 2 different colors, then n of k and the vector, the multinomial coefficient with n and then k, n minus k, is the usual binomial coefficient. Okay, but yeah, just be careful here that we're treating this as a multinomial coefficient, and typically k is going to be a vector or a list of numbers. Okay, and so just putting all this together, we find that this natural probability distribution on omega hat, these unordered samples with replacement, is such that on a single element, it has this probability, nk, then the product over the different colors of rho of a to the power of ka. Okay, and there we're finished. And yeah, this distribution has a name, which is, as you may have guessed, the multinomial distribution. Okay, and yeah, just this may have been sort of a bit difficult to follow. It's really good with this sort of thing to do some examples and also to have another look over the lecture notes. So yeah, check out the textbook for examples about this thing, and it'll make the formulas, this sort of thing, make a lot more sense. Okay, and let's go over an example. Okay. So suppose we've got an urn with some red balls, some blue balls, some green balls. Although I will delete one of those green balls and put in a red ball. Okay, so there are, well, n of red divided by n is 0.4, n of blue on n is 0.4, and n green divided by n is 0.2. Okay, and maybe we'll scale this up so that there are, say, 200 blue balls, 200 red balls, and 100 green balls. Okay, but the point is that, as we've seen, it whatever we figure out is only going to depend on these numbers. Okay, so, and then we ask, well, we draw 5 balls with replacement. What is the probability exactly for red? Okay, well, the natural sample space is what we've just introduced. So we're going to work with omega, which is sequences Ka in, well, vectors or finite sequences of non-negative integers, such that the sum over the different colors is equal to 5. Okay, and then our event that we're considering is A, which is K in omega hat, such that K red is 4. Well, we can explicitly enumerate these. These are, well, if we use the order red, blue, green here. So K equals K red, oh, K blue, K green. Well, then these are 4, 1, 0 or 4, 0, 1. Okay, this we can write as a disjoint union of its two single elements. Okay, so we can use sort of the properties of our probability measure and the explicit formula to figure out what we get here. Okay, so this is going to be row red, this is going to be row of blue, and this is going to be row of green. Okay, and well, let's just figure it out. So the probability of getting the set A is, well, it's just the probability of getting this plus probability of this. Okay, and then we just, so this can be 5 choose 4 1 0 times, well, we get 0.4 to the power of 4, we get 0.4 to the power of 1 and, oh, sorry, no comma there, 0.2 to the power of 0 plus 5 choose 4 0 1 0.4 to the power of 4 0.4 to the power of 0 0.2 to the power of 1. Okay, let's just evaluate these because they're the same. So 5 choose 4 1 0 is, as we've seen, it's 5 factorial divided by 4 factorial 1 factorial 0 factorial, which 5 factorial is 120, 4 factorial is 24, 1 and 0 factorial are both 1, so this is 5. Okay, so then you can plug this in a calculator or figure it out by hand, and you come to the answer of 48 on 625, or 0.0768. Okay, and there you've figured out the probability of getting exactly 4, sort of assuming that our model is all correct. Okay, now finally, I need to introduce some notation for this multivariate normal distribution. Okay, so typically you would sort of include all the numbers inside notation associated to this. So we're going to say that PA of A, we're going to give this the name M of N and rho of A, where N is number of draws, and rho, which is the vector rho A for A in E, are the probabilities of obtaining color A. Okay, and this is the notation that we're going to use for the multivariate normal distribution in this course. All right, thanks for listening.